Hello, today we are going to study the ocean tides. A good way of starting it is talking about some brilliant minds. In the early 17th century, Sir Johannes Kepler was a pioneer in suggesting that the tides were caused by the moon's gravitation around the earth. Galileo Galilei, also at the beginning of the 17th century, explained that the tides are movement was a consequence of the movements of rotation and translation of the earth around the sun. Have you ever heard about them? The first modern theory of tides was developed by Sir Isaac Newton to prove his law of gravitation. It is supposed that the Earth is perfectly spherical and totally covered with a uniformly thick layer of water for convenience. It explains very precisely the forces that act over the oceans. Thus, is neglected the continents and seafloor influence on the tides. This is the equilibrium theory. It's important, but couldn't explain the real ocean tides. The dynamic theory of tides, developed by Pierre-Simon Laplace in 1775, describes the ocean's real reaction to tidal forces. Laplace's theory of ocean tides took into account friction, resonance, and ocean basins' natural periods. It predicted the large amphidromic systems in the world's ocean basins and explained the oceanic tides that are actually observed. The equilibrium tide theory calculates the height of the tidal wave of less than a half meter, while the dynamic theory explains why tides are up to 15 meters. The tides generation can initially be explained by the law of universal attraction or the law of universal gravitation, spread in 1682 by Isaac Newton. It is one of the exponential laws of classical mechanics, a physics area basically invented by him. Every body attracts another body with a force that, for either of the two bodies, is directly proportional to the product of its masses and inversely proportional to the square of the distance that separates them. Isaac Newton. The modern version of this equation was described by Laplace, where F is the force of attraction, G is the acceleration of gravity, m1 and m2 are the mass of bodies, and d is the distance. In this context, the tide should be understood as the vertical oscillation of the sea surface or another large body of water on Earth, caused primarily by the differences in the gravitational attraction of the Moon and to a lesser extent by the Sun over the various points on Earth. Tide generation forces. The Earth-Moon system's gravitational attraction. The effect of the Moon is 2.25 times greater than that of the Sun, although its mass is thousands of times lesser. The centrifugal force resulting from the Earth's Moon system revolves around the center of mass, or Barycenter, located 1,500 kilometers below the Earth's surface. What is the Barycenter? In astronomy, the barycenter is the center of mass of two or more bodies that orbit one another and is the point about which the bodies orbit. It is an important concept in fields such as astronomy and astrophysics. The distance from a body's center of mass to the barycenter can be calculated as a two-body problem. If one of the two orbiting bodies is much more massive than the other, and the bodies are relatively close to one another, the barycenter will typically be located within the more massive object. In this case, rather than the two bodies appearing to orbit a point between them, the less massive body will appear to orbit about the more massive body, while the more massive body might be observed to wobble slightly. This is the case for the Earth-Moon system. In fact, Earth and its moon revolve about a common center of mass that is located on Earth. The Earth-Moon system can be imagined as having a fulcrum. The two masses' rotation is about this point. As with a lever, there is a balance when the mass of Earth times its distance to their barycenter is equal to the lunar mass times its distance to the barycenter. The motion of the Earth-Moon system barycenter forms the ellipse that is the orbit about the Sun. The orbit of Earth's center about the Sun is sinusoidal about this ellipse. The tidal forces acting on a single particle of water must be balanced. These forces are the gravitational attraction of the Earth, which is the same for all the water particles, the gravitational attraction of the Moon, which is stronger for those particles on the side of the Earth facing the Moon, and the centrifugal acceleration about the common axis. If these forces are added for all the particles of water on our hypothetical planet, it can be shown that there is a resultant vector in our sphere of water on the side of the Earth facing the Moon, where the Moon's gravitational attraction is greater. And there is also a resultant vector on the side away from the Moon, where the centrifugal force is the more dominant force. These resultant vectors are shown in this image as the tide producing force. This is a nice spelling word, CZG. When the tidal generating forces of the sun and moon are acting in the same direction, the resulting tide is higher. The high tides are higher and the low tides are lower, resulting in tides with greater amplitudes. These are the so-called spring tides. CZG is the astronomical word for the conjunction or opposition, especially of the moon with the sun. During the new moon, the attractive forces of the sun and the moon are added, resulting in the greater spring tides. In the full moon, the CZG is also the astronomical condition, and the attraction forces of the sun and the moon are still added, resulting in great spring tides. Quadrature is when the tidal generating forces of sun and moon act at an angle of 90 degrees concerning each other. The resulting tide is lower. The high tides are less high and the low tides are less low, resulting in tides with smaller amplitudes. These are the so-called neap tides. Neap tides occur in this quadrature when there is the first quarter moon and the attractive forces between the sun and the moon are in a 90 degrees angle. The same occurring during the last quarter moon, and the result is that neap tides are less important than spring tides in the oscillation of sea level. At the coast is the place where the tidal oscillation can be seen by our eyes, and there is the low tide, the ebb tide, the flood tide, the high tide, and we are going to talk about those terms and definitions. The Earth's rotation will cause the same point on the surface to pass through different tide levels over the course of a day. Thus, there is a repetition of the same tide level approximately every 12 hours, what we call a semi-diurnal tidal cycle, since its period is half a day. However, the translation movement of the moon around the Earth causes a small delay of this recurrence of levels, and the period changes to approximately 12 hours and 25 minutes. As we have seen, Earth's two tidal bulges are aligned with the positions of the moon and the sun. Over time, the positions of these celestial bodies change relative to Earth's equator. The change in their relative positions have a direct effect on daily tidal heights and tidal current intensity. The Earth's tidal bulges track or follow the position of the moon and, to a lesser extent, the sun. As the angles of these two celestial bodies in relation to the Earth increase and decrease, so do the tidal bulges. Here we observe the moon's changing declination to the equator and the effect that this has on the positions of the Earth's tidal bulges. This This is a north-south cross-section through the Earth's center. The ellipse represents a meridian section through the tidal force envelope produced by the Moon. So, comparing the Moon at higher declination and the Moon with no declination directly over the equator, we can see some tidal patterns like diurnal tide, mixed tide, semi-diurnal tide, equatorial type. And before we go into those tidal patterns, let's see some tide terms, some definitions about tidal oscillations. Here we have some description of the tides and some tide important terms. The first one is the hat, H-A-T, that is the highest astronomical tide. The highest tide which can be predicted to occur. Note that meteorological conditions may add extra height to the hat. Then we have the mean high water springs, MHWS, the average of the two high tides on the days of spring tides. Then the mean high water neaps, MHWN, is the average of the two high tides on the days of neap tides. The next one is the mean sea level, MSL. This is the average sea level. The MSL is constant for any location over a long period. The mean low water neaps, MLWN, is the average of the two low tides on the days of neap tides. And then the mean low water springs, MLWS, is the average of the two low tides on the days of spring tides. And finally, the LAT, lowest astronomical tide, and the CD, charge datum, the lowest tide which can be predicted to occur. Some nautical charts use this as the charge datum. Note that under certain meteorological conditions, the water may fall lower than this, meaning that there is less water than shown on charts. And this is critical for navigation. Please take a closer look for some more information in this image. And if you have some doubts, make further research on that topic. The intertidal zonation and ecology aspects. Each region on the coast has a specific group of organisms that form distinct horizontal bands or zones on the rocks. The appearance of dominant species in these zones is called vertical zonation. It is a nearly universal feature of the intertidal zone. To illustrate that, let's see some of them. Firstly, we can talk a little about the high tide zone or high intertidal zone. This region is only flooded during high tides. Organisms found there are anemones, barnacles, chitons, crabs, isopods, mussels, sea stars, and sea snails. Then we can illustrate the mid-tide or mid-littoral zone. This is a turbulent zone that is covered and uncovered twice a day. The zone extends from the upper limit of the barnacles to the lower limit of large brown algae. Common organisms are snails, sponges, sea stars, barnacles, mussels, and crabs. Finally, we can talk a little about the low tide zone or the lower littoral zone. This region is usually covered with water. It is only uncovered when the tide is extremely low. In contrast to the other zones, the organisms are not well adapted to long periods of dryness or to extreme temperatures. They may die. The common organisms in this region are brown seaweed, crabs, mussels, sea cucumber, sea lettuce, sea urchins, shrimps, snails, and tube worms, and so on. Take a closer look at the image to see some other zones like the spray zone and the lowest low tide zone. Some further important terminology is the tidal range, that is the vertical distance, normally in meters, between consecutive high and low tides. The flood tide is the time interval during which the sea level rises from low tide to high tide. And the ebb tide, that is the time interval during which the sea level drops from high to low tide. If the Earth were a perfect sphere without large continents, all areas on the planet would experience two equally proportionate high and low tides every lunar day. The large continents on the planet, however, block the westward passage of the tidal bulges as the Earth rotates. Unable to move freely around the globe, these tides establish complex patterns within each ocean basin that often differ greatly from tidal patterns of adjacent ocean basins or other regions of the same ocean basin. Three basic tidal patterns occur along the Earth's major shorelines. In general, most areas have two high tides and two low tides each day. When the two highs and the two lows are about the same height, the pattern is called semi-daily or semi-diurnal tide. But things can get more and more complex. Let's see what's happening. This map from NOAA presents the distribution of tidal range patterns around the global coastline. The red lines represent semi-diurnal tides. The yellow line represents diurnal tides, and the blue line represent mixed semi-diurnal tides. An area has a semidiurnal tidal cycle if it experiences two high and two low tides of approximately equal size every lunar day. An area has a diurnal tidal cycle if it experiences one high and one low tide every lunar day. An area has a mixed semidiurnal tidal cycle if it experiences two high and two low tides of different size every lunar day. The place I live, southeastern Brazil, experiences a semidiurnal tidal cycle. Take a closer look in this map and try to find out how is the tidal pattern of your coastal region. These are the appearance of a diurnal, semidiurnal, and mixed semidiurnal curves. In the first one, diurnal tide, there is one high tide and one low tide a day. The cycle has approximately 12 hours and 25 minutes. In the second one, the semidiurnal, there is two high tides and two low tides with almost the same height during a day. The time interval between each one is something about 6 hours and 12 minutes. In the third one, the mixed semidiurnal tide, we have also two high tides and two low tides a day. The interval is almost the same, 6 hours and 12 minutes, but the height of the tides can vary significantly between each cycle. And those are 4 examples of a monthly tidal oscillations. The first one is semidiurnal form, the last one is diurnal form, and the second and third are mixed forms. Beyond those tidal patterns, there is some harmonic constituents which are very important in predicting tides. Gravitational forces acting on tides change as the Earth, Sun, and Moon change their relative positions. We can visibly see these position changes in the Sun and Moon's rise and set, the Moon's changing phases, and the changing seasons of the years. Each of these changes is cyclical, repeating over time, and each change also has a measurable effect on the tides. There are hundreds of periodic motions of the Earth, Sun, and Moon identified by astronomy. Each of these constituents in a set of harmonic constants is a mathematical variable describing the effect that cyclical motion of the Earth, Sun, Moon systems has on tides. There are 37 components which normally have the greatest effect on tides and are used as the tidal harmonic constituents to predict tidal conditions for a location. Here is some of them. M2 is the largest lunar constituent. It is related to the direct gravitational effects of the Moon on the tides. The Earth rotates on its axis every 24 hours, but the Moon is orbiting in the same direction as the Earth's rotation. It takes a location on the Earth an additional 50 minutes to catch up to the Moon. This results in a tidal signal, M2, which has two peaks every 24 hours and 50 minutes. S2, the largest solar constituent, is related to direct gravitational effects of the Sun on the tides. The Earth rotates on its axis every 24 hours. This results in a tidal signal S2, which has two peaks every 24 hours. Sa is solar annual constituent. It's related to the changing positions of the Earth and Sun on an annual basis every 365.25 days. In this table, there are some more of these tidal constituents with their names, period in hours, relative amplitude, type, and origin. While the International Hydrographic Organization Tidal Committee recognized more than 140 long-term longitudinal and semi-diurnal constituents alone, high-quality tidal predictions can typically be achieved including relatively few constituents in shallow water and other situations where nonlinear interactions between primary constituents are strong. Compound constituents such as the M4 component can become important. Finally, each harmonic constituent provides the mathematical values which describe a specific cosine curve. Tide predictions are a calculation adding the effects of each of the 37 cosine curves to produce the predicted tides complex curve. Take a look in this example. As the tidal range is the vertical distance between consecutive high and low tides, there's some tidal range classification that is important. First, the microtidal environment is where tidal range is lower than 2 meters. The mesotidal, the tidal range between 2 and 4 meters. The macrotidal, the tidal range is higher than 4 meters. And finally, the megatidal are environments where tidal range is higher than 8 meters. This map illustrates the global distribution of tidal ranges. The continents are in white. The microtidal areas are dashed in blue, the mesotidal environments in red, and the macro and megatidal locations are in gray. Some examples of the largest tidal range can be illustrated. The first one is in Fundy Bay, Canada, where tidal oscillations are up to 17 meters. On the Amazon coast, the tidal range can reach 8 meters and can range also up to 8 meters in the Korean Peninsula in the Yellow Sea. the open ocean, the tidal waves would have a wavelength on the order of 20,000 kilometers and a period of a bit over 12 hours. The tidal waves are thus shallow water waves everywhere on the Earth. Frictional drag on the sea floor leads to loss of energy, and shoaling and refraction affects the speed and direction of propagation. In practice, ideal tidal waves racing freely around the Earth do not occur. Instead, standing waves are generated within ocean basins and semi-enclosed seas, and this leads to the formation of amphidromic points. Amphidromic points are points around which the tidal waves rotate. If we consider a tidal wave within a closed rectangular basin, the wave will travel across the basin, reflect off the far wall, and then interact with other advancing tidal waves. The result is to produce a standing wave, which the highest vertical motion or amplitudes of oscillation at the boundaries and a nodal point where there is no vertical movement. Also associated with the standing wave is a horizontal movement of water which has its maximum excursion at the nodal point and minimum at the boundaries. Because of the Coriolis effect, the water motion is deflected towards the left in the northern hemisphere, producing an anticlockwise rotation about the nodal point or amphidromic point. In this animation, we can see the rotation of the water levels on the ocean basins. Take a closer look and maybe you can see that the red represents higher water levels, the blue represents lower water levels, and see if you can identify how do they rotate on the ocean basins considering the northern hemisphere and the southern hemisphere. There are a significant number of amphidromic points in the world's oceans that control large-scale tidal motion, and on the continental margins, smaller amphidromic systems come into existence as a result of a complex interaction of tidal waves associated with these larger systems and coastal topography. Enough for today. See you soon. Take care and be safe.